Okay, so we want to do some practice with the photoelectric effect. So I brought the simulation back that we were using last time to introduce the idea to, and we have some light shining on metal, nothing's happening, because obviously our frequency is too low, our wavelength is too high. So what I'm going to do is I'm going to just start, see if we can get some things going here. So I'm going to make the wavelength smaller to increase the frequency to see if we can get enough energy coming in. And we'll see when things start jumping here. We're in the purples already, going pretty good. It looks like we're going into ultraviolet. Still nothing's happened. Let's see, go a little bit smaller. And go small. There we go. Now we got some electrons jumping. Okay, so I want to try and back this up as much as I can, and until electrons aren't jumping off anymore. So I'm at 323. Oh, looks like 323. If I go, oh no, so there's one. I'm going to back it up a little more. 331. What I'm trying to do is I'm trying to get the electrons to stop so I can get right to that boundary point, that threshold. Now it's really slowing down. I got 337. Here we can make the intensity a little brighter. Looks like 337. So if I go to 331, yeah, I got electrons coming off. I'm going to go back to 334 actually. Now I still got electrons coming off. I'm going to come to 337. And hopefully no electrons come off. All right, so it looks like it's 337. So this is that boundary wavelength. So right now, if I go any higher with the frequency right now, I'm going to get electrons coming off, which means right now I should be at threshold frequency. So I'm going to sort of sketch this out here. We got this piece of metal over here. We got the piece of metal. So there we go. Got a piece of metal right here. And we've got, I'm going to use purple for the ultraviolet stuff coming in. All right, so it's coming in at 337 nanometers. So apparently this is my threshold wavelength is 337. So with that idea, I can then find my threshold frequency, because of course threshold frequency is going to be that divided by the threshold wavelength. So all I have to do is divide the two out and I'll have my threshold frequency. So if I do that, I've got 8.90 times 10 to the 14 hertz. So that's my threshold frequency, because if I make the frequency any higher, I get electrons coming out of it, which means right now the energy is going in, and all that energy is going in and being absorbed by the material as the work function. So when we're at that perfect boundary like this, this must be right where the work function is. So if I found the energy of this, if I found how much energy at threshold frequency right here, so I got that frequency, so if I multiply that by Planck's constant to get the energy of those photons, we've got about 5.90 times 10 to the negative 19 joules of energy. And this would be, I'll convert this to electron volts, because we often like to use electron volts for this type of thing. So if we convert that to electron volts, we're looking around 3.69 electron volts. And since we're right at threshold frequency and we've got no electrons, and this is right at that boundary point, this must all be going right to the work function. So now I know the work function for my material must be 3.69 electron volts or 5.9 to the negative 19 joules. Because if I change the frequency at all, if I make the frequency even just a little bit higher, I get electrons coming off. So I'm right at that boundary. Okay, so that's what I got going on right here. So let's do that. Let's take this and increase the frequency to get electrons coming off. So if I take this now and increase the frequency, maybe, they're got a wavelength of like 240. Look, I easily got electrons coming off here, no problem. Okay, so let's modify the question here a little bit. Let's change the wavelength to 240 nanometers. So what I want to know is, what is the speed of the electrons coming off? Okay, so let's look at this. And again, we were talking about this before. It's all about energies. It's energies, energies, energies. It's all about adding and subtracting energies. That's all it is. So I'm just going to start by finding the energy of my photon. Now, if I find the energy for my photon, that is just hc over lambda, or you can use hf. It doesn't make any difference. And let's see how much energy I have coming in with my photons. And I remember I changed it to 240 nanometers, just like in the simulation. Okay, so let's see how much energy I have coming in. And this gives me 8.28 times 10 to the negative 19 joules, which is more than my work function when I was at threshold frequency of this. So I know that the electrons are going to come off. So I got 8.28 coming in. The material is going to suck up 5.90 as the work function. So the leftover energy, which is around, 2.5 or so, that's going to be the kinetic energy electron. So the kinetic energy is going to be the energy that came in from my photon, subtract the work function energy, which is right here. So I'm going to subtract the work function energy. So I'll take that 8.28 and I will subtract that 5.9, and that'll tell me how much kinetic energy was left for my electron. So that leaves me with 2.38 times 10 to the negative 19 joules. So the photon came in with 8.28, 5.9 went to the work function to pay off the material, and then the electron was then left with 2.38 to the negative 19 joules. Now that I have that, I can find out how fast it's going, because that's just the kinetic energy. So I can take this and make that equal to good old 1/2 mv squared for the electron, the basic kinetic energy, and then I can solve for how fast. This would be like the maximum speed possible for the electrons. So with that idea, I'm going to then take this and I'll find out how fast the electrons are going. So it's using basic 1/2 mv squared, mass of electron. Should get a speed around 7.2 times 10 to the 5 meters per second. So that would be the maximum speed possible for the electrons. We just do the maximum speed because it's the easiest thing to do. Okay, so that's basically how this works. Find a couple energies, add them, subtract them, whatever you need to do, and that's it. It's pretty straightforward. Okay, so let's do another scenario here. Let's do another question and see what we can come up with. All right, so let's try this one. We're going to use copper, and I know the work function for copper is like around 4.94 electron volts, and that's what's actually set up in the simulation here. I'm using copper in the simulation this time, and I'm going to say the electrons coming off at 7.66 times 10 to the 5 meters per second. We're looking for the wavelength of the light that was coming in to begin with, and I'll see how close it actually matches up to the simulation here. Let's see how close we can get. So again, this is all about energies. So I'm going to try and find my energies as best I can. Now, first things first, I've got that 4.94 electron volts. I would definitely want to convert that into joules to make things a lot easier. So if I do that, that's like 7.904 times 10 to the negative 19 joules of energy. So there's my work function right there. So I had to convert that. I've got the kinetic energy of the electron. It's definitely solvable because I have got the speed of the electron. So let's use the 1/2 mv squared, and I can find the kinetic energy of the electron. And that gives me 2.67 times 10 to the negative 19 joules. Okay, so I've got my work function energy. I've got how much energy was absorbed by the material. I've got the kinetic energy of the electron. Of course, both these energies came from the photon to begin with. So to find the energy of my photon, I just have to take those two and put them together. So my photon energy must be the combination of the two. So I'll take my kinetic energy and I'll add my work function energy, and I'll put those two together. And we're looking at around, we'll round off a little bit, around 10.6 times 10 to the negative 19 joules. Got a little extra one in there. Oops. Get rid of that one. There we go, that's better. Okay. All right, so now that I have that, I can then find the wavelength. This is going to be equal to hc over lambda, and we will just have to solve for the lambda. So that'd be hc over lambda. Got the h, got the c, I got the energies. Let's find out the wavelength of the incoming light. That gives me 1.88 times 10 to the negative 7 meters, which of course is 188 nanometers, which is exactly what the actual simulation is showing. So that's pretty cool. Okay, so again, that's how this works. Just find the energies. Sometimes you add, sometimes you subtract, and that's all you have to do. So it actually works out pretty well. Okay, so let me show you something else with this. Let's try out one more question. Well, actually, I guess it's not really a question. I'm just going to show you something that Einstein did. Now, notice there's actually like a little power supply down here. Now, what is that for? Well, let me show you what that's for. What Einstein did is he had, light shining on here, and you got the charge going across. This actually a little battery right here, a little cell right here, and you can actually put an electric field in here. You can't show the electric field. I don't know if you can see, there's a little negative showing up on this plate and positive on this one. You can actually make an electric field and charge the plates, and when you do that, it makes the electrons go faster across, because obviously they're repelled by the negative plate and attracted to the positive. But the thing is, you can also do the exact opposite. You can actually reverse the polarity, and when you do that, you can actually get the electrons to slow down. And this is what Einstein did, because what he wanted to do is you have the current reading in the bottom right-hand corner there. What you want to do is you want to increase the electric field between the two plates in order to stop the current. Okay, so I'm going to keep on going. It's getting harder and harder for them to get across, and then we'll see how close we can get. Oh, there it is, 0 at 2 volts. Okay, now this is really important because the electrons are fully being stopped. No electron can actually make it to their plate. Now, this is what Einstein did, and I'll show you what he did with this. Now, you've got the two plates, something like this. You charge this one negative, and you charge this one positive. We've got the photon coming in, and the electron fires across, but the electron doesn't make it. So what he did is Einstein actually used an electric field in order to stop the electrons. Okay, he used an electric field. Okay, so he applied a voltage or potential difference to create what's called stopping potential. Okay, and this was actually called stopping potential. And basically what happened is actually a really, really simple idea. He uses the electric field to do work against the electrons and take away all of their kinetic energy. And that's what the stopping potential is. So the electrons have kinetic energy equal to 1/2 mv squared. And what he did is he used the stopping potential, the potential difference, the voltage, to take away that kinetic energy. And I told you something. And of course, if you guys remember, energy for a charge in between plates is equal to QV. So he would apply the voltage in order to stop the electrons. And since they're perfectly balanced, he knew that 1/2 mv squared was equal to QV, and that is the stopping potential right there, that voltage right there. Now, why would you want to do this? Well, really simple. You know what material you're using. You know the energy of the photons coming in. So he knows, you actually know the photon energy. Okay, so you know that. You know the photon energy, the energy that's actually coming in. You now know what the kinetic energy is by using stopping potential. So you use the QV in order to actually find the EK. Well, if you know the photon energy coming in and you know the kinetic energy of the electrons by stopping them using the stopping potential, you can actually subtract in order to actually find the work function. And this is how he could find the work functions of metals. Because actually knowing the speed of an electron, that's pretty much impossible. I mean, you can't see them. They're so fast, it just doesn't work. So he would indirectly use an electric field and what he called a stopping potential in order to find out how much kinetic energy was being taken away. So therefore, if you know the energy of the photons going in, you know the energy being used to stop the electrons from actually making it across, the stopping potential, you know the kinetic energy, you can subtract the two to find the work function. That's a really common way to find out work functions. Just let the electrons come off, find out how much work or energy is required to stop them from making it across, and then use the difference between photon energy and the energy being taken away from the electrons in order to find the actual work function for the material. Okay, so that's what stopping potential is. So it's kind of neat, taking the energy away to sort of like find it by just taking it away. So it's kind of neat how that actually worked. Okay, and of course, if you increase the voltage even more, then of course it's really hard for them to get off at all. It's a really strong electric field.